Alright, welcome to my first video. In this video we're going to play around with the ARM exception handling, and the title is ARM exceptions, gotta catch them all. This idea came to me during work. One of my co-workers had to implement some exception handlers, and he had to test them, and some of them are a bit harder to trigger because they're hardware faults or stuff like that. And that sounded like an interesting challenge. So in this video I'm trying to trigger as much exceptions as I can and catch them, and we'll see how far we'll get. So I prepared some things. I prepared a Rust project that can build for the ARM chip that I'm targeting. So I can show that now. So I have a hello world. The code is here, and we'll use this as a starting point to get the exceptions going. Yeah. So this is on a STM32L4. Let me see. What is it? Nucleo board. But it doesn't really matter what exact chip it is, because we're only going to use the ARM specific things. So these registers that we're going to use and these features are available in all ARM chips, and in this case it's in Cortex M4. Alright, well, let's get started then. Yeah, I was thinking let's first get some easy exception handler going, and maybe it's nice to show all the exceptions. So I download the reference manual of this chip, and we have the what is it? Nested vector interrupt controller, so the interrupt controller. And I think this somewhere has a table with all the exceptions in it. Maybe not. It looks like I downloaded this a bit small. Like this is not enough pages to be the real thing. So let me look it up. Cortex M4 reference manual. Now this is what I got, so this is not the correct one. Maybe this? No. Technical reference manual. Let me see. Must be somewhere. Blanking right now. No, this. What is it called? ARM Cortex 4? I don't know, man. This is way too small, right? most of the time these documents are like hundreds of pages, not only 100. Or is this complete? Some of the registers. Nah, no way. No way this is it. Okay. Nah, off to a great start. Technical generic user guide. What is this? Maybe models. No, still not it. Resources in one place. Architecture. This is still the technical reference manual. So, what is this? No. Oh man. Architecture, maybe? Give me this. What's it called? Is this it? Maybe. Let's see. PDF. This is the web thing, right? Oh, this is the PDF. 900 pages. Kijk. Alright. This is promising. Let me see. Instruction set. Legacy stuff. No. Application model. Interrupts, faults. Here we go. Maybe. This exception model, yes. Alright, here we go. Alright. Overview of the exceptions that are supported. Well, so reset, non-maskable, hard fault, mem-manage, bus fault, user fault, debug monitor, the SysVCall, this is for supervisor, so this is typically used by operating systems. And then there's some interrupts. PendSV is also typically used for operating systems, and the SysTick is a timer. Alright, and the SysTick was the thing I was thinking to start with, because we can easily trigger it via by setting up the timer and waiting for the thing to trigger. So let's try that. Back to the code. So in order to do that, we have to configure some stuff in the core. And in Rust this is done via the Cortex-M package. So the Cortex-M has something to take the peripherals. Let me see, I think it's this one. Steal, take. Take sounds steal. Alright. Yeah, maybe call it core. Let's see what we have on this. So we have all kind of peripherals, and in this case we are looking for the well, we have to look it up. So we're going to target the SysTick, and I guess that it will be somewhere defined in this manual, so maybe just look for it. SysTick, is this the correct? Yeah. SysTick, this one. So here we go. It only has a couple of registers, so it's not that hard to set up. It's in the SysTick thing, so okay, that's easy. What do we have? We have control register, I guess. Oh yeah, control status register. We can enable it. Sounds like a good idea. Source implementation defined. Yeah, so most likely enabling the thing would be enough. Count flag. Oh, here it is. Yeah, okay, not that important. So we want to enable. This is done with a write, or how does this work again? Oh, yeah, we want the control register, and then we want to write. Okay, this doesn't have the nice listings for the bits, I guess. Oh well. Where is the modify? Modify. F1s. No, alright, so that's just not supported for this register. Typically, or not typically, but there are packages that have a similar interface but provide nice wrappers to set bits or subfields within a register. So I was looking for that, but apparently this is not implemented for this register, so we just do a direct write, and we will set the enable bit. The other bits should not matter that much. All right. Then we have the reload and the calibration. Calibration isn't that interesting, I believe. Core. That was the reload. Right. I don't know. Let's do something like 1000 hex. I don't know. Okay, what's up with the and save? Yeah, sure. So we add that. All right. And what is that complaining about? out also unsafe. Okay. Maybe just move everything into unsafe because we'll keep running into this. Right. We also have to enable the interrupt itself, I believe, and this is done with the NVIC. So I lost that one. Where did it go? Well, conveniently right after this. Okay. So here we have also a couple of registers. Let's see. This is the overview. Yeah, okay. So there are multiple groups of registers, 0 to 15, for each of the different features. So we have interrupt set enable, interrupt clear enable, set pending, clear pending, interrupt active bit. So we want to enable the interrupt, so that will be done with the set enable register. So this is ESAR, okay. core.nvig.esr. Right. Let's try for this one. Modify if this has the special stuff, but I'm not sure. It's not picking it up. Oh no, it's just a U32, so that will not work. We'll also write this directly. So we want to look at what interrupt number this is. So yeah, this has some calculations. Okay. Oh, wait a minute. This is the... Okay, so we have to index this as well. Sure. I think this stuff is just implemented with some logical numbering, so yeah. So I think this is... What am I looking at? Bits are reserved. Okay. Aren't there some nicer dot? I thought there were some nicer functions for this. Yeah, here we go. Set priority request. What's request? Request. This sets the pending interrupt. That's not what we want. We want to enable it. Well, maybe just enable? Didn't. Into borrow priority. Deref. Unfortunate. So there is a set priority, but there isn't an enable. Okay. Strange. Clear object. now we'll just do it this way, I guess. I thought there was a better way to do this, but maybe just look at the documentation of the Cortex. Cortex M core, because I feel like there should be a better way. Interrupt, enable, yeah, here we go. Okay. What is this? Oh no, this is the global interrupt enable. No, that's not what I wanted. Interrupt number. Right? Yeah, disable all interrupts. No, that's not what we want. We want peripheral register. Oh, this is how I'm supposed to do it, I guess. So let's do it that way. Instead of stealing it, taking and wrapping, yeah, that's at least somewhat nicer. Maybe look at an example in there. Git repo. Git Cortex. Cortex and Git. Something like this. Yep, here we go. Test suite, do they have some examples? Doesn't look like it, at least not directly, maybe here. No source. Maybe here, examples, yeah. Unsafe hard faults, oh, sounds promising. No. Exceptions. Oh, at least here's the SysTick stuff, so we can take that already, because we're gonna need it anyway. This? No, it doesn't look like it. Entries. Yeah, maybe not. Maybe the nice stuff is only implemented for in the hull of the chip itself. Maybe we should look there. Maybe we should just add the ST hull to the project, and we can use some easier methods. Let's see. List. Yeah. Yeah. Let me see. Let's call this the F4. No, this is not what we want. We want. I thought I fused all these things. So we want. I think it's this one. Yeah. Yeah, okay. Let me. Yeah, this goes to crates. So the L4, this one, and alright. Let me just copy that one. Add it to our table. Okay. And let's go to the documentation. I hope this is giving us the stuff we want, but let's see. What did my chip end in? 2. Nah, this is all the enumeration of interrupts. Yes. Clone debug number. Yeah, maybe this was a bad idea. Maybe just we just do it raw, something like this. Okay. I think there was some special initialization needed for the SysTick, but I'm not sure about that. And this, we need to verify what interrupt number this should be. So we enable the interrupt. Oh wait, we can just set the pending flag, right? So no need to just to be sure everything works, we can add some printf from here. So make it hello from SysTick. Sure. We need the exception. Yep. Why is it green? That's not. Oh, it's an error. Yeah. What's going on? Is it confused? Maybe it's confused. Because oh, somehow it's thinking this is the enum, but that's not a capital E. Weird. Alright, so it's not happy. Yeah, right. By okay, fair enough. Where did my manual go? So this one. Yeah, this one. So it was somewhere here. No. Oh yeah, I clicked through something. Here. So here we have the numbers. Maybe I should just copy this stuff. Oh, so it was 15. All right. So let's dump that here. And it was 15, assuming it's in this, in the 0 register, in the 0th element. And instead of, oh yeah, we enable it and then we just set it pending. And right, we're also going to duplicate this. So this will be, and this will be the hello world, so that's fine. We set the pending interrupt, so interrupt pending, I guess, pending register, is that correct? Priority, no. So it was set pending register. Yeah. Yeah, okay, so we set up pending and then, okay, let's see if this does at least something. So what we expect to happen is the program starts, it prints the hello world. We enable the SysTick interrupt and we set it pending. That should trigger this exception handler. That should print this hello. It should return, I think, the bits automatically cleared and the code continues with the end and then we loop. And then we're done, essentially. So let's see. Let's run it. Right, so yeah, not exactly what we wanted, but it's also strange it's not printing the end, right? What's going on there? Oh yeah, I should enable interrupts itself. So let's do that as well. I think they're default. Yeah, I think they're getting disabled by the startup code. So we could do that with core text. Wasn't RT in flow. That's your problem. Oh, maybe I should remove that then. No. Okay. What? It was an interrupt, right? What am I missing? This one. Peripheral, no. So we're looking at Cortex M. It should be in interrupt enable. So should be able to call it. It should be in and save, so let's do that here. Are you happy? Looks like you're happy. Let's try again. Still nothing. Okay. So yeah. It seems that maybe I am triggering an interrupt, but not the correct one, and we end up in an exception handler that's not defined, or the default exception handler, and typically that's implemented with a for loop and an endless loop. So that could explain why we don't see the end, that we don't return and we don't see the end printed. So if I try to eliminate this set pending stuff, this set pending right, then yeah, we don't set the interrupt, so interrupt should never run and we should see the end. So let's try that. So let's see. So yeah, okay, so this works as expected. So if we enable this, we set some wrong register that we are not. Yeah, we're doing something that's not quite right. Okay, what am I messing up? Something with the interrupt numbering. Oh, okay, they started. I see. They start at 1. Typically stuff starts at 0, so let's make it 14. Let's see what happens. Alright, here we go. No, still nothing. Unfortunate. Alright. What's going wrong? So we want to set the interrupt number. Okay, you just have to look better at the NVIC stuff. That was just around the corner from here. So let's scroll down a bit. Right? Maybe not. Chaining, yeah. Oh, it was. It's unfortunate that it doesn't track in the index where you are. So we're in B3. So that's here, right. So we want to set enable. So how does this actually work? Oh. So they start from what? What's up with this? Huh? Yeah, something's not quite. No, alright. No. Just close this stuff. This is not. This can also be closed. This is the big one, so it should be something in here. Somewhere in here. Implemented interrupts. Operation. SysTick. Okay, let's read this stuff. Maybe it gives a hint what to do in order to set to get the interrupt thing. Oh. Yeah. Yeah, sure. That would be necessary when we want to use the timer to set the pending flag. So when we get back to using the timer to trigger the interrupt, we should also set this bit. So let me already add that. So that makes this. Let's use binary and make it 1 1. So alright, so that's already then fixed for when we get there. But in order to get the interrupt, yeah, we should enable the thing and okay, wait a minute. Do I have let's see. Alright, yeah, I have an idea. If we add the default handler here, we will see the default handler. And if this is what's happening. So I believe that we just trigger an interrupt that's not the interrupt we want to trigger. So we trigger some other exception than the SysTick exception. So that's getting switch to, so that's being called, but that's not implemented, so it calls the default handler. So if we overwrite the default handler, we should see at least our custom message. So let's try that. Handler. I think it's default handler, but yeah. Build gives signature and save. Oh, it gives us a number. Right, that's convenient. So we can see what's being activated. So let's also print that, I guess. Yeah. Okay, that build, let's run it. Yeah, so okay. So the 14 is correct. But apparently SysTick is not number 14, so what's going on there? What did I miss? So try 515. Oh, wait a minute. No. Yeah, maybe 15. I mean, we had that already, but maybe we changed another thing. I don't know. Let's try. Yeah, so we still get the default handler, so something's not quite right. The SysTick. Oh, okay. I think I know what's going on. Maybe. Yeah. Let's add it anyway. So the Cortex series of chips, they have, not all of them, but the M4 has it. It has a VTOR, virtual interrupt offset table or something like that. I don't know. But what that does is it allows you to place a table at offset in memory, and maybe this offset is not correctly configured. So no, that would not work because we do get into the default handler. Huh. So that would imply that the offset is correct, but the SysTick is not. Oh, wait a minute. Shouldn't this be SysTick handler, maybe? I think it gives an error when it's wrong, so it should have already errored out, but yeah, nothing. Okay, so it was correct. Why is it blue? That's weird. This is not. Okay, so what's going on? We do get the interrupt, so it's only handled by the default handler. We get the correct number, 15. A bit strange. Maybe the exceptions are not in this bank of registers, because the chip does make a sort of divide between exceptions and interrupts, and the core has a number of exceptions, so that are these 15 or 16, yeah, 15, and then you have the vendor specific implementation, and they provide a bunch of more of interrupts for the peripherals. But I thought these were just a continuation, right? So they start at with these ones and then count forward. So, but maybe that's not totally correct. Yeah, sometimes they're also negative. Oh wait, this is an signed number, so they could be negative. So yeah, maybe this is not exactly what we want. Are there more registers in this thing, right? So interrupts. So let's see what this has to say about interrupts. Doesn't really seem to say a lot about it. Yeah, that it has this tick int pending, but not some initialization routine to get stuff working. So what has this to say? So let's see. Each register corresponding. Yeah. So this is, looks like this is really talking about interrupts, and we have to look at the exceptions. So where's that stuff hiding? Let's take a peek at this. This sounds familiar. Debug core, so that's not it. And this one sounded familiar, but auxiliary. Hey, interrupt controller type. Nah, that's not it. Is that everything? Looks like it. Unfortunate. This one also sounds familiar. Clean. Yeah, here we go. Alright, this is what I was looking for. Yeah, these were the enables. Yep, here we go. Okay, so we have an enable, and yeah, we can just use this exception to enable the thing, but I think we don't get, we lose the pending, the set pending register, because that's not available for exceptions. Yeah. Oh, what is this? Calling this function will do nothing. Huh? Okay. Sure. What else is there? We have disable, enable, and I thought that also was a priority thing, but set priority, yeah. Okay, so let's take that one. So, and comment it out because we don't need it for now, but maybe we need it in the future when we're starting to have multiple interrupts, but for now we just want to trigger the interrupt. Okay, so maybe maybe just look at this thing in the datasheet. So what is it called? It's called SVCall. I don't see it here, so control block. Is this it? Interrupt type, software triggered, no. Yeah, maybe. Here we go. Here's also the Vitor I was talking about earlier. But we want, I think this one. Nope. Configuration and control, no. Handler priorities, yeah, that's interesting, but maybe for later. These are false, active, is active. Ah, and it's pending. So let's read what does active mean. Is active that it is happening or that it's enabled? The pending is that it is, yeah, pending, but I don't know. Maybe other bits that look interesting. Not really. So we have the SysTick is active. Sounds like it's active. That when that bit is set, it's like in the interrupt handler. So in the exception handler. So yeah, maybe just, so this is just wrong, so we can remove it. That was for the interrupts, not for exceptions, so confused myself there. Let's try this. So now we have enabled the interrupt. Maybe it does something, I don't know. Oh yeah, this works. Okay. Cool. So we catched our first exception. Oh my god. Let's abort this. And let's verify that this ends up as a negative in the default handler. I'm interested in that. So we should expect a default handler with -15, I think. -1. Huh. Okay, so maybe. Okay. Maybe it counts down from this. So this is -1, -2 till -16. I don't know. Kind of weird, but all right. The first exception is catched. So yeah. So in order to, because what I want to do is I want to chain these exceptions. So I want all exceptions on one big call stack. So in order to do that, I have to trigger the next exception that I want to trigger in the exception in the current exception handler. So well, let me show you. So I want to, yeah, maybe just follow this as, oh no, that won't be that easy, but maybe we should keep this order from the bottom up. So we're now here in the SysTick handler, and yeah, the next would be the PendSV, but for now I'm going to focus on this one, the SVCall, because I think that's an easy one to trigger, so we can test this this idea. So we want to continue from here. So we're in this exception. We want to continue. Yeah, the exception stacking. So we want to trigger the next exception here. And first, let me disable the SysTick, so we don't get a lot of continuous exceptions. So here we get continually the exception. That's not what we want. So in order to prevent that, we just do it one time and we disable it afterwards. So if we add that, oh yeah, this is going to be painful. Yeah, so let's not use the core, just use, we're going to use the, yeah, escape hatch things. So here there are also these same peripherals that, how did it work already? Right, you can, thought you could get this stuff. Oh yeah, like this. You can get to the peripheral without owning the core. So yeah, so the Rust borrow checker and the ownership model is used to model the registers. So this takes ownership over the peripherals, or at least it's modeled in the type system like that. So this core, this peripheral, yeah, thing, variable, has ownership over the peripherals, but it's kind of difficult to transfer that ownership from the main into this exception handler. So we're going to avoid that. So we're going to use an escape hatch, and yeah, I have to think about how that's done already, how you do that, but it should be possible, because yeah, these registers are just global, yeah, just memory mapped in the global space, so we can just peek and poke into them and that should just work. So the library should provide some methods for this that you just can yeah, just take them, just peek and poke into them without the ownership, so sidestepping the whole ownership thing. And that's what we're going to do. And I thought it was something like somewhere here. So we take the register block and then, no, what do we have? Maybe I'm too deep. So peripherals, and I thought it was this marker. What do we have on this? Pointer. Get. Oh, there's already also some nice functions. Maybe we can just use them. Huh. Alright. So it would be disable interrupt, I guess. Mute self, yeah. So we need this constructed somehow, but how do we do that? Like this? Oh yeah, this gives the block. So let this. Nah. Nope. This is not it. But it had to be. Sounds familiar, but. Not quite sure. From get into deref? What does that do? We have to Google this one because let's see. Maybe just look through this documentation. Yeah. So we have the peripheral. Let's see. This is not that important. No. Register maybe. No. So here. Yeah, take unwrap. Modules, structs. Yeah, so we want to get access to one of these things without going through peripherals. So we need some constructor for this, but yeah, I suspect it's unsafe. Yeah, everything is already unsafe, but this also sidesteps the yeah, something like this. Something like this. Deref self. It has to do something with this, but I'm not quite sure how these things fit together. Maybe let's try something. Yeah. What's in this? Or oh, this is the same thing. Right, this is where we want to be. We want to get this thing. And this is already the marker, but so we want a constructor for this. But it's not really there. So this. I want to deref this? I don't know, man. But this gave us a raw pointer. So, oh, no, like that, and then we need some name for it. SysTick is. Can we do this? Alright. Alright, at least we got a register block, but is that what we want? I don't know. Yeah, that looks like what we that looks like it is what we want. So yeah, we can use that to clear the bit. So this one, and we just clear it. So write 0 into it. This can be removed. Is this allowed? No. It's not happy. Maybe we don't deref it. Just, and then this is unhappy. Yeah, I imagine. So this should also be unsafe, I guess. Not like this, but let's test it first and then we can change. No. What is it complaining about? To deref it at that point? Sure. And save. Yeah, sure, this is already unsafe, but okay. Will this work? I don't know. Let's see, where did we end? So yeah, this was the previous thing where we disabled the SysTick handler, but now I expect the SysTick handler to trigger. We get in it, we print, we disable the thing, and we fall out of it. So we only triggered once. So I expect to see a single hello from SysTick, and then the end. So let's run it. Yeah. No. What? Alright. So the end triggers before the SysTick. Oh yeah. Maybe this takes some time before. Yeah. So we set up the timer, but it only triggers somewhere in the future, and this code just continues and it gets to the end, it prints it, and then only after it's already spinning in this loop, the timer expires and triggers the SysTick. So still plausible, but at least we only see it once, so that's fine, good enough. Let's clean this up a bit. So yeah, it's already unsafe, so we can remove these. Not really happy about this, but yeah. Not quite sure how I did this in the past, because it must have been a better way. Oh well. But for now we have what we want. We start the timer, trigger the timer, disable the timer, so we see it only once. Right, now we can try to trigger the, what was it called, SVCall? Yeah, SVCall. So this should be pretty easy because it's done via an instruction. So we can just use that. So that's somewhere in core ASM. Core. Oh, that was ASM, but ARM? Oh, ARC. Yeah, ARC. Yes, here we go. And it's just SV call, I guess. I think this gives you can give this a number. So let's give it a number 1, I don't know. So this is going through the assembler and stuff, so, and in my experience it gives pretty good error messages, so we can just try to build it and see what's going wrong. So yeah, it's not happy, invalid instruction. Okay. Well, let's look it up in the manual, what it's supposed to be. Don't know this stuff from the top of my head, so instruction details. Instruction set, this one. Miscellaneous, maybe? Yeah, supervisor, oh, SVC. So without the call, and then it gives an immediate aid. And what's this C? Condition, right? Standard assembly fields, CN, yeah, condition pass, so we don't use that. So it's just CSV. CS, what? CSV? SCV? SVC, okay. SVC, number 1, sure. Build, yeah, it's happy now. Run. Nothing happened, okay. All right, I guess we have to enable this as well, so let's look in the same place as where we were before. What was it called? Not the S, but the core. This one? I don't know. I think it needs some kind of enable as well, maybe. This we didn't need. So give this, does this give any hints what is required for this to be called? No. Call supervisor, yeah, sure. This is the, alright, maybe look here. Accept behavior, no. Exception. Permanently enable and has configurable priority, so yeah. Maybe it's not happy. Oh, maybe the priority is not correct, so we're nesting now, so maybe the default priority isn't sufficient. So if we try it here, maybe it will work. What you complaining? Let's remove this. Run. Yeah, so this, yeah, this triggered it. So something's messed up with the priority. So with this chaining, we need to make sure that the priority of the next exception that we want to trigger has a higher priority or lower, but at least it gets triggered. So we have to set those up as well, so those registers as well. But just issuing the instruction is enough to trigger the exception. We see it here as -5. Is that correct? So yeah, it looks like it's counting backwards. So -1, -2, -3, -4, -5. Yeah, so this, yeah. So yeah, looks correct to me. But let's add it as a real thing. So we don't use the default, but we use the SVCall directly. So let's do that. And so I guess it's called SVCall. Yeah, maybe this also gets the number that we give it. I don't know. Let's copy this and PendSV Alright, let's see what we get. Yeah, okay. So that works. Nice. So the next thing would be to fix the priorities. So let me re-add this here. So this, it's still strange because, yeah, what would happen? Why would it hang on this? I mean, yeah, maybe that's just the implementation. It has to happen here because it's an exception and cannot really be delayed, because then, yeah, you get some weird stuff. I mean, yeah, the exception really has to happen here. But if for some reason the priority is preventing it, maybe that will result in a hang. So, interesting. But we're not quite sure that hang. Maybe we should change this to trigger earlier, so. We can for now just do it here. I'm not that happy with that, but we can remove it afterwards. So yeah, okay. So it really hangs, and without this, it won't, I guess. Didn't we just spam end? Yeah, okay, so it's spamming. Yeah, okay, so it really hangs on this point, but that's nice place to continue. So we can remove this one because we know that works. And now we have to figure out how to continue the exception stack and keep chaining them, and let's see where we end up and how high we can get this exception stack. So yeah, my guess is that priorities are incorrect, or maybe they're the same, so that's why it's preventing this from running. So let's look at the documentation. And figure out if there is some, yeah, exception priorities and preemption. Here we go. So yeah, reset, NMI and hard fault are executed fixed priorities. -3, -2, -1. Alright, so the lower the more priority it has, I guess. Software assigned priority values start at 0. Yeah, okay. So we can start at 0 and we can increase them, so give them lower priority. So we need to give very low priority to our SysTick. Yeah. Okay. Cool, but how do we change that? this is the priority grouping. So, oh yeah, so you have fields and subfields. Yeah, so there's some configurability in the core. So you can choose to have exception, or at least that's for interrupts. I don't know if it's also for exception, but it seems like it, because group priority and subfield priority. So you can have a group, and if an exception in the higher group is triggered, then it will go to the next group. And within the subfield, you have exceptions that can be in the same group. There's there are similar priorities in that aspect, but you have sub priorities. So if both are triggered, and the chip decides to go to that group for processing, then it will look at the sub priority fields to figure out the individual the priority in between the exceptions within the group. So it's like a tiered, multiple tiers of exceptions of priority handling. So you can have the group priority and then the subfield of the sub priority. But we're not going to need that, so we can have that set to 0, I guess. So not really used, and we have to set that to 0, but I guess that's just the default value, so don't have to look into that, I guess. But I would expect that somewhere around here there would also be a reference to the register that is used to enable these priorities, or at least location where I can find them, but maybe I'll just look around in the code and see what looks right. So we're in the what is this? This is the SCS. Really? No, SCB, yeah. So let's see, core SCB dot, let's see, what do we have? This was the stuff where the priority was. Oh wait, now we can use the priority. Yeah. This one. All right, here we go. So the prio. Unsafety, yeah, whatever. Prio U8. So we want to give lowest priority. So the highest number, because 0 or -3 had the highest priority. So a lower number gives higher priority. So we want to give a high number, so it has low priority, and then we want to give it the SysTick. So what is this type? System handler. System handler. Where does this go? Bus fault. No. SysTick. So we want to give this a high or a low priority. Maybe just include this because this is. Yep. Mutable, sure. Make it mutable. Yay, happy. Okay. Build it. Alright, run it. Let's see what happens. Oh, the end still. Oh yeah, that's this stuff. I'll try again. Hey, it triggered. Nice. So we triggered the second exception. but we never returned from it, so I'm not sure what's up with that, but cool, I guess. Oh no, we did return from, but we never print after it again, so maybe we should fix that and maybe just I don't know, how should we do this? I don't know where we end up, right? So if we chain these exceptions, do we ever return from them? Because if we return from them, then we can add some additional print or something like that. I don't know. Maybe we just set a flag. Yeah, let's do that. Let's add a done flag that we set and we check for it, and we printed one, we printed done. Yeah, that sounds like a good idea. So let's do that. I'm going to use a static done. We use atomic bool. Sure, why not? Atomic bool, new, and we initialize it to false. Yeah. Right. Then in this we can set it to true. Done. Store true. Ordering. Relax, nice, sequentially consistent. So like this. So we use the flag. Now we can use if we set the flag, and when we when in the loop we can pull it, and yeah, let's have the final loop that's just the blocking of the loop forever, the wait forever, because we cannot return from main. So this one is mandatory, and here we can have a while and we can try to just read the done flag. Done. Fetch. Read. Store in. Load. Ordering. So the sequentially consistent is the strictest consistency, so it's always correct, so just use that, or not always correct, but at least it's most strict, so that way I don't have to think about what the ordering should be. But maybe this could be acquire, I don't know. For now this will work, so we'll loop while we're not done, and this can just be this, and then we can move this to here. Let's see, does that work? So what I would expect to happen is that now we trigger the SysTick, that triggers the SVCall. That sets the done flag, and the done flag will fall through the core will fall through as well, and we'll print the end. So now we will have a better ordering than that the end happens first. That's a bit strange, but let's see if it works. Yeah, it works. Right, cool. So now at least we have a nice ordering, and we can check if return from all the exceptions. Because if they never return, we never get to this end. So let's test that. So let's see if we add an infinite loop here. We would expect, not here, I wanted to add it here. So if you prevent the exception from ever returning, so we keep looping in it, I would expect that the end is never printed. So let's test it, and if it works, we can use that as a validation for our next thing. So yeah, that seems to be working. Nice. All right, we have 2 exceptions. Man, didn't think it would take this this long, but we're making progress. And we're doing everything from scratch and without much libraries, or at least all the registry poking is pretty manual. Oh, this is a helper, but implementation should be pretty straightforward. Yeah, a bit of math. Yeah, sure. We'll just use it for convenience. Next up, yeah, we skipped the PendSV, so let's try to add that in between. Yeah, sure, why not? So this one is typically used to do the context switch, or to do something OS related, and it's typically done in between the normal code and the interrupt. So when an interrupt or an exception has happened, so the context switch has been made, that would be that's a convenient point to inject. That's not the context switch. How do you call it? When an exception frame has been created, that's a convenient place to do a context switch of the operating system. So the ARM core provides a dedicated exception for that, so the pending. And don't know how it works exactly, but you can use it in a higher exception. You set the pending, and then when eventually all exceptions are handled and you're going back to the regular code, so normal code, then the save it pending triggers, and then you get to switch something around or whatever, do what you want. So I wonder if that's always the case. So if you always have to have it at the end, so always at the boundary of exceptions and normal code. Because if that's the case, we're going to have a problem, because we want to have SysTick as our first exception, and then the pending SV. So I don't know how that's going to work out, but we'll figure it out. Let's see. Yeah. Let's add the exception handler for PendSV, then SV. And this one, yeah, like I said, it can be set by some other exceptions. So this is typically done by, maybe there's an instruction for it, but I think there's also setting a bit somewhere. So let's look. Yeah, where should we look? I guess it's somewhere in the SCP. So let's look around in here. I think it's maybe this. pending. On write sets favorite pending a section as pending. Is this it? And it can be removed. So yeah, I think this is it. So alright, this is an interesting register. So are all these things on write? So yeah, this is on write, no effect. Guess it's also write only, yeah. So I think we can just do a write to this, ignoring everything else in it, just setting the bit we want, and we set the set bit. So when we write this bit, we set the pending flag. Okay, let's try it. So it's in the ECSR. Okay, let's first try it here, but core SC E CSR. Right, and then we want to write bit 28. Right. Yeah, I think that's correct. Sure. What is this? PendSV set? Oh, ST SysTick. Oh, okay, so we could also use this to trigger the SysTick interrupt. Huh. No, we don't need that because we're already starting the timer and have it triggered like that, so that's fine. So this should work, but we don't want to trigger it here. We want to trigger it in the SysTick. Yeah, we want to trigger it in the SysTick. So let's see. Let's trigger it in the SysTick. Let's trigger it here, and then we can see if it when it happens. That will be interesting. So we have to do the same trickery as here. So I guess we can copy this part mostly, and then we need the SCB, and then we can replace this with SCB. Like this. This really sucks, but should be a better way, but I don't know. Let's see. We just let's build, sure, and then to see what happens. All right. Oh, we still have. Okay, it's already interesting. So we still have had our infinite loop in the SysVCall, so that's not what we want. So that's why we don't see the end, but we also don't see the PendSV. PendSV. So setting this or didn't work, or it did not immediately trigger the PendSV. So maybe this is also a priority thing, or maybe it's just only getting called when all the exceptions are unwind and we get back to regular code. So let's see what happens. We remove the infinite loop, so we can now run it again. And it still hangs. Interesting. So maybe that's also the priority issue. So let's also add PendSV to the list. Yeah, maybe we have to play around with this. Maybe the SysTick has to be higher and then the PendSV has to be lower, but It's not the order that I want actually, so I don't know, let's see. Oh, at least we get to the end, but what? Huh. Oh, yeah, the done is set by this. Oh, and here's nothing. Oh my god. Let's at least print something. No, let's look again because... Hey, okay. What's going on here? PendSV. Huh? Why does it get triggered here? What? Really strange. Maybe you should clear it? Just to be sure? Let's print that thing, because maybe it's already set. Oh, I set it. Right? Yeah, this is the leftover that I didn't copy. If I remove that? Yeah, everything is alright again. But the question is, where does the SysTick... Oh, right. Yeah, maybe, yeah, okay. So we want to see, now we see the ordering, but we don't see in what context it is happening. And I want to stack all those exceptions. So we can visualize that by just adding not only an entry print, but also an exit print. So we add a done from SysTick here, and we can add a done from SVCall, and yeah, this doesn't really contain much, but for completeness, let's see. So I'm really curious where the PendSV happens within the stack. So yeah, okay. So this isn't what I want, but maybe it is expected. So the so we're in this SVCall. Yeah, this still has the, I guess, very high priority, default 0, so this is highest priority, highest configurable priority. So this sets the, right, this sets the bit, or where am I setting the bit? Oh, I'm setting the bit in SysTick. Oh, that's not what I want, but even then, we are leaving SysTick before the PendSV is called. So yeah, but that's also expected with equal priorities. So the PendSV can never interrupt the SysTick because they have equal priorities. So I wonder what happens if we increase this priority, and this least significant bit made it the subgroup thing, right? So we want to increase with 2, I guess, or decrease. So like this. Let's try that. So now it at least has a higher priority than SysTick. Maybe it will trigger immediately when we set it pending, but I'm not sure. No, it did not. So I'm afraid this will only trigger on leaving an exception. So we can never have this chain. That's unfortunate. Let's see if that's true, because now we'll add this not in the SysTick but in the SVCall, I guess. No, I want, oh yeah, I want this to happen first, and then this should be moved to here, and then priorities are still, yeah, not totally correct, but should be good enough. So let's see if this, what does this? Yeah, this enters the SysTick and leaves it. Then the unwinding of the SysTick frame, that triggers the exception of the PendSV. So yeah, I think that we cannot, that's just how the thing works. It's designed to sandwich in between, yeah, to chain off of an exit of another. It will never interrupt. It will never. It will never interrupt something that's happening. It will only happen when the exception frame gets unwind. So yeah, I think we would have to accept this as a feature of the chip, or limitation, or in this case it's not exactly what I wanted. I wanted to stack all the things and have the context, have them all wrap each other, but it seems that it's not possible. So oh well, we continue from here. Let's see. We have we have this, and we chain into this. This is reserved, so we skip it. Debug monitor. Yeah, that one is tricky, because I'm not actively using the debugger, but I'm using something to flash it, right? So I don't know if it interacts with that. And I'm not that familiar with the debug monitor, so maybe we should skip that one and continue with SVCall. That one we implemented. Then a bunch more of reserved, and then the use fault. So I think this is, yeah, for now let's continue with this. This is where the interesting stuff starts to happen, like real faults and violations and stuff like that. So that's interesting. And the debug monitor, it's also interesting, but yeah, maybe I should look into it. Yeah, okay, we will do the debug monitor. So I believe this is used to implement software debugging facilities. So it allows you to get an exception when you hit a breakpoint. And then you can have a software implementation that does something and potentially can continue and have that all run on the chip. So it is interesting. So okay. So how I think this should work is debug monitor. Yeah. Yeah, okay, let's look into it. So we want to, how much? I'm already almost 2 hours. Yeah, quite thinking to not go for much longer than 2 hours. So don't think we get far with this, but at least we can try something. So how I think this should work is that we we set a breakpoint instruction and we just let it trigger and see what happens. And I guess we have to configure the debug core as well to catch it and to take care of it, but for now we can try this. So instead of, okay, let's copy this in its entirety, make it debug monitor, then we get the SysCall and SVCall, and here we want to just add a breakpoint, and I think it's just break. No, there's something with a T in it, something like this. But no. ASM break pt. Is this it? Are you happy? Yeah, it's happy, but we can use just lose the direct assembly. That's fine. Alright, let's see what this does. Oh, interesting. So I'm using, yeah. It has the trampoline. Load. Yeah, so I'm running the application with what's it called? ProbeRS. So let's see where it is here. So I have the runner configured with ProbeRS. So that's a utility that allows you to program and run. So that's what you see here. Never explained it, but cargo builds and links the application, and then a runner with the run subcommand. It will look for the runner, and the runner is configured to use ProbeRS, and that will erase, program, and start the application on the microcontroller. And it's using RTT. What's it called? What does it stand for? I don't know, but it's a protocol that you can use to transfer data from the microcontroller to the host PC via the debug interface, and that technology is used to do the printing. But it seems that it also take care of interrupts. So ProbeRS also shows a nice stack frame of a backtrace with all the stack frames, or at least some locations that were on the stack during that happened. Yeah, when it encountered the breakpoint. So, and this is in conflict with the software, with the exception, the debug monitoring. So I believe you can only do either via hardware probe, do the debugging, or use the monitoring and do it via software on target on the chip itself. So I think this is also a dead end. So that's unfortunate. Yeah, okay, for now we will skip it. Oh man. My plan was to chain them all, but doesn't seem like it's going to happen. At least not with this setup. So, but it's fine. We just continue when we go to the usage fault. It's also interesting. So I have to disable this. This is no longer needed, and we can use the SCV call to go from pending into SCV call. Maybe I should reorder this one and have them in logical order, chronological order. So, and maybe add some comments here. This was this label SysTick, and this was set PendSV bit flag, whatever. And this with capitalization, something like this. All right, I'm happy with this. Next up, usage fault. So we're going our way backwards through all the exceptions, and usage fault is the next one. So let's copy this and update the prints. Now we need to trigger a usage fault from this one. So this can be removed. And we need to if we want to trigger a usage fault here. And how do we do it? What is a usage fault even? What does it entail? So let's look it up. Exceptions somewhere here. Debugger behavior. Oh, this is the. No, we skipped it. Here and then usage fault. All right. Usage fault. The usage fault handler. Fault handles non-memory related fault caused by instruction execution, undefined instructions, invalid state. Okay, undefined instruction is the easiest. I think there exists one. It's also generated by Rust. At the end of each function or something like that. It's some not safety, but it's a good practice to have unreachable code be represented by an invalid instruction because it will crash the CPU. So I think there is one, but let's Google for it because I don't know that off the top of my head. So on invalid instruction. This one. UDEF. Yeah, it's even as a mnemonic, or what's it called? Mnemonic. Sure. Yeah, let's try it. Doesn't seem that in this story there's support, but 11 years ago, so maybe it has been added or it's more common now. So like this. Let's compile it. Oh, it's happy, so let's try immediately. Yeah, maybe this is again the priority. So let's add it here. This should be yeah, oh yeah, we missed, yeah, so we didn't add the SV call here, and that should be yeah, minus, let's make it a bit more clear, -4. Sure, and let's immediately add the user fault there as well. So we have that already there for the next one. Let's try again. So now the exception of the priorities should be correct. So the SVCall exception handler has a lower priority than the usage fault. So when we trigger the usage fault now, it should switch to that. So let's see. No, and we broke something else because the PendSV is not happy. What? Maybe the priorities thing is not configured correctly. So I assumed it was 0, but maybe it's not. Maybe it isn't. So let's see where it is. It was somewhere, I guess. Also, let us see B. What was it called? Maybe it has a function. Would be nice. Access mode? No. Thought it was in this one, but wait a minute, but we broke the SV call. No longer is called. So, and this also wasn't, oh yeah, that was after introducing the, yeah. So let's see. Auxiliary. I want the, maybe it's here. Active pending, no. Vita, no. Yeah, there was some kind of register that determined how the priority bits were interpreted. And what was it called? Something prio. Prio nog wat. Prio. Oh. And no, priority escalation. Priorities, exception, yeah, somewhere around here. Let's see. Yeah, this one. Maximum support. Prio group. Prio group field. But where is this located? In this Prio group. Yeah, alright. All right. Okay, this looks. I see a key. All right, this seems complex to change, but maybe look at resets to 0. So this should be correct. So 0 is yeah, 0 is only one subfield, one subbit, subpriority bit, and the remaining 7 bits as group priority. So that shouldn't be the issue then. If we have it like this, but it seems like it is an issue. Let's see what happens if we increase this by a lot. So get halfway. It doesn't work then. Yeah, then the call we get into the call. And if we then set this to the highest priority, do we get there? No. Usage fault. Did we add it? Yeah, we did add it. And it's happy with this instruction, even though it's undefined. So we should trigger the usage fault, but we don't. All right. Yeah, this is also maybe where we start to get into the specifics of the chip, because there's also things like an exception in an exception leads to an NME. So, but if that's the case, we should see that as well. But maybe we should hook that. Yeah. So let's add a handler for the NME. NME. Is that correct? NME. So, but no, that should be covered by the default handler. We didn't see that, so maybe it's not. I don't know. Would expect it to be. It's not happy with that. NME. And maybe. No. Okay, how is this implemented? Non-maskable int. Okay, sure. Happy now? Okay, what happens? No, we don't see it. So this would be nice if we can break in here, but not sure if that's possible with probaras. It has a, if I recall correctly, it has a GDB flag for the run subcommand. I thought it had. Maybe not. Oh, here, run GDB server. Okay, you can try that. What does this do? Because if it's only a GDB server, I still need GDB itself. I don't think I have that installed, so that will be an issue. Let's see if we can at least run this. So, oh fuck. No, here. Yeah, and then target. Come on. It's called Cortex. Temp. Debug on like that. It's not happy. Why are you not happy? Debug. Yeah, this has some leftover test files. I should remove them. Should be correct then. Unexpected argument found. Don't have to give a target file? What's up with this? Option. Oh. Alright, so you don't give an executable in elf. So you just like this. Yeah, but I don't have. Yeah, this is not useful. Maybe I have it installed. Alright, so yeah, what I want to do is I want to just set a breakpoint. Let's see if we run it. Where did we end? So if we send a breakpoint somewhere, or I could at least break into and step to the debugger. But I don't have that set up on this machine right now. So I think this is where I will end the video. Yeah, let's recap. So let's see. I think we got pretty far. So we triggered the SysTick, the PendSV and the SVCall, and we were able to chain them. Not the PendSV, because that only can occur during a exception frame pop, or I don't know how you call that, transition. So when you when you leave an exception handler. So that's why we cannot chain that. Maybe we can trick that. Yeah, that's okay. That's one thing I still want to do then. We can trick it by maybe using SysCall to set it, return from the SV call, then it will trigger, and then we can use another SV call, so we can use the numbers for that. Yeah, maybe next time. That's something we can do next time. But for now, yeah, pretty happy with it. We got not quite as far as I hoped, but we're making progress, and yeah, I think it's interesting. So thanks very much, and bye.